All right, I'd like to take a few minutes to kind of talk about the central limit theorem, go back through this process again that we're doing, the theoretical foundation for the statistics that we're doing, because it takes a while to get used to it. And I think one of the things that's kind of confusing is the fact that we have multiple means and multiple standard deviations. So the idea is that there's some sort of population out there that has some sort of characteristic that we're looking at. So in this case, we're looking at some sort of numerical data where individuals in your population has some sort of number associated with them. We'll talk about mu there as the population mean. If we were to add all those numbers together, divide by the number of values we have, that tells us what mu is. And then sigma is the notation that we use for the population standard deviation. And to start with, it's nice to assume that this distribution is roughly normal. It doesn't have any outliers. It turns out that if your sample size is large enough, it doesn't really matter what the shape of that population is. But in general, that it's maybe roughly a normal distribution with a mean of mu and a standard deviation of sigma that are out there. And so what we're doing with the central limit theorem is you're looking at, so what we want to know is we want to know about this population. But the idea is that there's too many people over there to measure everyone, to get this number off of every single person. It's costs too much. It's practically impossible. By the time it takes to do it, maybe the population will have changed. So it's kind of hard to say. So what we're going to do is instead we'll take a sample of these. We'll select some of these to be over here in a sample, some sort of random set of those. So you might have like 21, 28, 15, 12, 32, different values that you're going to choose at random out of your population will become a sample. And then out of that sample, we'll compute a sample mean, and S, which is the sample standard deviation. In there, and then that's the one that we calculate with the square root of the sum of the x of i's minus x bars squared over n minus 1. Whoops, that n minus 1 should be underneath the square root. So let's try to make that included there. So you calculate your sample standard deviation there in there. But what happens when we look at the central limit theorem is we think about the sampling distribution. What would happen if we were to take multiple samples? So if I look at sample number 2, I get a different group of things. Sample number 3, I'll choose different ones, and maybe somebody will end up, maybe this 15 would end up in both those samples, and that's okay. But the idea is that each one of these will produce a slightly different sample mean and sample standard deviation, and so we'll get maybe this would be 1 and that's 2, and this should be 2 and 3 and 4 and 3. 3. Okay, so you've got different. Each sample will have a slightly different mean because it will be made up of slightly different peoples. And what the central limit theorem tells us is that we know what the shape of that distribution is. If you look at the distribution of the x bars, it should be a normal. With the mean of the x bars equal to the mean of the population. So if you look at what's the average of these sample averages, so if you look at all the different possible samples you could come up with and find the average of those averages, so it's kind of a double average there, it turns out that average should, according to the central limit theorem, work out to be the exact same thing as the population mean. All right, so that's good. But if you're looking at these x bars, how do these x bars vary from one x bar to the other? and that we get the standard error for the mean, excuse me there, or sigma sub x bar. And it turns out that the standard deviation of the x bars is related to the population standard deviation divided by the square root of your sample size. So there's three sort of standard deviations we're talking about here. There's the standard deviation of the population, that's sigma. There's the standard deviation of an individual sample. So when you randomly choose 5 individuals or 8 individuals or whatever that is, you can calculate the standard deviation of that sample. And then there's the standard deviation of the sample means. And so then you're looking at, each sample produces a different mean, and how do those means vary? Are those means the same? How do they vary apart? And that standard deviation is sigma over the square root of n. All right. And we've done a lot of stuff using the normal distribution so far. We've looked at hypothesis tests and confidence intervals using this normal distribution and t-score and z procedures, where you'd calculate a z-score or a t statistic or a z statistic to do a hypothesis test in there. Okay, but in practice, what really happens is to do that, we have to assume that we know what the standard deviation of the population is, and we usually don't do that. We don't know what that is. In practice, we don't know, if we're doing a confidence interval or something like that, we don't really know what the mean of the population is. We don't know what the standard deviation of the population is, but what we do know is the sample mean, and we know the sample standard deviation. And so what we do is we just make that assumption that when we're doing that, we're going to say that the mean of the population is about going to be the same as the mean of our sample, whatever we got as our sample. But we add in a margin of error to account for that. So if you're doing a z procedure, it would be the mean over the standard deviation, or z star times sigma over the square root of n, to get an approximation for what the mean of the population would be. Okay, but again, a lot of times if we don't know sigma, probably the best thing to do is to use s as an estimate. And again, we almost never know sigma. We almost never know. We don't have data from the entire population. We can't calculate the standard deviation from the whole population, even though Excel or your calculator will spit one out. That's not really this population standard deviation. It's you're looking at a subset of the standard deviation. So we want to use that S number that comes up there. And so what we do, it turns out though, if we're using S instead of sigma, instead of having a normal distribution, we end up with the t distribution. Or sometimes called students' t distribution, or Gosset's t distribution. The t distribution was developed by a guy named Andrew Gossett, who was a quality control engineer for the Guinness Brewery in Dublin, Ireland, and he approximated a way to. He used his statistical knowledge to monitor the quality of the hops and the fermentation process, and so. Using a small sample sizes and sorts of things, and he came up with this t distribution there. The Guinness Brewery did not want him to publish his results; they wanted to keep him private, as a trade secret. But he did it anyway. But he sent it to journals with a pseudonym with the signature of student. So that's why it's sometimes called the student's t distribution or Gosset's t distributions. But it's still the t distribution in there. So anyway, that's what it comes with the t distribution. The t distribution is bell-shaped like the normal distribution, but if you've got your normal distribution here, whoa, that's a pretty ugly line. Let me see if I can fix that here. That if you've got, let's do it maybe in red here. So if you've got a normal distribution here, whoops. All right, so here's your axis. Maybe here's your normal distribution, your standard normal, your normal distribution in there. What happens when we do a t distribution? Come on, let me change my color of my pen here. There we are. What happens is the center remains about the same, but you end up with more area out here in the tails. The peak's not as high, and you end up with more area out here in the tails. And there's different t distributions depending upon your sample size. So it has more area in the tails than the normal distribution. So if you go out to like a z-score of 2, the area underneath the curve will be greater for the t distribution than the normal distribution. And the shape depends upon n on your sample size in there. So the shape depends upon your sample size in there. So you have to get the right t-score. So it takes a little bit more work to find the right t-score. You got to look it up in the correct table. And I believe we've got other videos showing you kind of that process. But the big idea is that our t distribution is what we end up with when we have to approximate sigma. We don't know the standard deviation of the population. We have to approximate it with the standard deviation of the sample. And we'll calculate things. Things will look a lot the same. That our confidence interval will be mu is equal to x bar. But instead of a t, instead of a z, we're now going to use a t star and s over the square root of n in calculating our confidence intervals. And we'd calculate a t-score doing a hypothesis test, x bar minus mu. It's almost the same way that you do it with a z-score, but we're using s over the square root of n in there instead of sigma over the square root of n. And so that's going to give us a slightly different thing. We have to look it up on a different table. We have to use a different cumulative probability density function to find that, to find the t-score, to find the p-value associated with that. But the whole idea, the whole process is still the same. We're looking at, what's, in a hypothesis test, if we make an assumption that we know what the mean is, and then we look at the probability that we can get the sample that we came up with just by random variation, just by random chance. What's the chance that I got a sample with a mean of 12 when the population really has a mean of 15? Is that statistically significant? Is it unlikely that I'd get a 12 just by random chance? Or, is it that's kind of what we're looking at with the hypothesis test. Or we're gonna make our interval a little bit wider to accommodate that we don't know the standard deviation of s. We're going to use a t-score instead in there. Okay, so I hope this kind of helps get the conceptual sort of thing and the idea of when you're going to use t procedures versus when you're going to use z procedures, and it all depends upon the standard deviation. If you know the standard deviation of the sample, we're going to use the t, and you can always calculate the standard deviation of the sample. But if by chance we're given the standard deviation of the population, if we're given s or sigma, then I get to use the z score in there. So it all depends upon the standard deviation. Are you calculating the standard deviation based on the sample, or do we have some assumed value? Do we know the standard deviation of the population? But the math is pretty much the same in terms of what you're calculating in there, finding your your z-score with the hypothesis test or finding your t-score with the hypothesis test. The procedures are essentially the same. It's just a difference of which one are you going to use. All right, t or z. And again, standard deviation is the key.